already talked about the signature assignment. We also have a signature assignment, which is due on Tuesday.
Yeah.
So, oh, were you talking about this one or another one?
No, we were talking about the history.
Oh, okay. Yeah.
The history one, that's like 3 assignments that go along with it.
Oh. Yeah. Make sure that you also do this one. We're not taking time in class to do it. Okay. So, pre-lab 12. Let's go to the Weaver State Canvas. We're going to 11:15. Also, I am caught up on grading, so turn in any signature assignment, turn in any labs, and I'll get them graded that day. Unless it's like at night. I'm not grading at night.
11:59 p.m.
Yep.
or 11:08 p.m.
Nope,
right?
that's not. That's not what I'm doing. So. I'll grade it the next day. Let's see, where are we going? Modules. So this is the last lab. Very exciting. Unless you take another chemistry class or another science class. Let's see. We are going to pre-lab. Oh, let me hand out the instructions. So I'm going to give everyone the instructions. You can read these.
Wow.
Excellent.
It's almost like I watch you.
No, you didn't watch it because she walked me through everything.
Oh, so this is
Our technician was
Yeah,
Oh, maybe I should be nicer. We were so there.
Yeah, I was really good.
well, I helped her through the entire thing. And she's
I know.
taking
It's
over.
because ours was like barely, ours was barely clean.
You were with us. You were beside me. No,
Yeah.
she walked me through the entire. Oh, actually,
Yeah.
thanks, Jake. Yeah, but it's like the doing the lab. This is for the Jake. It's the doing the lab that she said was good. And you didn't really help me beta.
Yeah, we actually did a good job.
We actually did do a good job.
Thank you.
Actually, you didn't, because like your titrations were very pink. And it should have been like,
They were.
They were kind of
We
pink.
redid them.
We redid the
Oh,
three.
Yeah, because it was, we
It's
messed up a
okay.
couple.
It's okay for us to be very.
Okay, so you have two things. You have your instructions, and then you have the data table. Okay. So in the instructions, it walks you through what's expected, and it kind of gives you some background. So this is a little bit different. This lab is you are hired. Your team is hired by a town, which is on the map. And you have to analyze these water samples and tell them who is polluting the water, okay? And you have to use evidence to support what you think, because probably if one of these, so we've got gravel pit, private landfill, town landfill, gas station, if they have to go after one of these people and say, like, you need to fix your practices so that you're not polluting our water, then they're gonna have to have pretty strong evidence to do that. So this is like a report. You're going to be writing a report explaining very clearly who you think is responsible for the pollution, and you need to support your answer with evidence. Okay? All right, so I think hopefully in class you'll be able to finish writing this. Okay, so there's lots of things going on. Your contractual obligations on page 2. You are to conduct an investigation of the groundwater in the region, looking for areas of contamination. In order to use your time efficiently, you will need to organize tasks. So who's going to be in charge of what? There's graph analysis, so somebody's going to color arrows, draw arrows, write a key, so that legend. Someone's going to be the letter writer, and someone is going to include a pH table in the lab. Okay, so each lab group is a separate company. So you're trying to be better than all the other groups, okay? Because this town, maybe they're gonna hire you next, but if you don't do a good job, they're gonna hire someone else next time, okay? So this says it will be done in partners. This is, Weaver State said this is going to be in 2s or 3s. Okay, 2s or 3s. Each write-up needs to include pH measurements. You're going to put these on the map. and mark it with colored pencil and shade the areas with the correct pH. You're also going to include a key or a legend to help the people who are reading this know what color is acidic, what color is basic, is there anything that's neutral, help that stand out. Also, you need to determine the direction of groundwater flow using the well monitoring data and a topographic map. So on this side, it's a topographic map, page 2. Are you okay? You need to move? We need to have you move. We can do that. We have lots of space today.
No, you can hold down.
Okay, let's see. So let's look at the topographic map for a minute. So flip to your topographic map. Have you ever read a topographic map before? What do the lines mean? Or what can we learn from this map? What are we trying to understand?
There's a river down the center.
Okay, there's a river. Okay, good.
The circles are wells.
Okay.
Squares are surface water.
Okay,
As it says in the key right here at the bottom.
good. Okay, very good. So what do these lines on the topographic map mean? So flip to the back, the figure 2. So this is the topographic map. So what does it mean if the lines are closer together? Do you know? Yeah. So if the lines are closer, that means it's steeper. Good. If the lines are further apart, that means it's flat. And then look at the labels on the edge of the lines on the edge of the map. So it says, mine on the left, it says 95, 90, 85, 80. So that's the elevation. We were debating what it's in last class, but don't know for sure the units, but that's the elevation, okay? Yes, it does say kilometers down here, but I think that's the distance. Could something be 95?
Yeah, okay.
I don't know. Does that make sense for something to be 95 kilometers in elevation? I don't know. Maybe it does. I don't know. Maybe we should look it up because I always think in feet.
Yeah.
Okay. So it probably could be elevation. I'm not sure.
That's definitely not elevation. That's just the side of the map.
Okay. And it's not necessarily near us. It could be like by the ocean. So maybe it makes sense. Okay, so if the lines are closer together, that means it's steeper. What happens if you put water on a steep slope? It's gonna go down. Yeah, and that's why the river kind of goes the way it does, right? Because it's in the flat part. The river's gonna run through the flat part, and the river is probably going to run downhill. Okay, so using this map, you can use this as evidence to explain why. So if one well has a high pH and nearby it also has a high pH, you could explain it looks like it's moving downhill, probably. Does that make sense? Or like if it's above a site, if the pH is high above the gas station, but not by the gas station, it's probably not the gas station, right? Does that make sense? Like,
yeah. Okay.
So you can use that kind of reasoning in your paper. Okay, and this is what they want you to use. So you're labeling pH here. You're going to shade where the pH is like high or low. Remember, low pH is acidic, high pH is basic, around 7 is neutral. We talked about that. Okay, what else? Okay, let's go back to our instructions. Determine the direction of groundwater flow using the well monitoring data and a topographic map. And we talked about the lines. Water flows down to the steepest areas to the river. So the one thing you have to do is identify the problem area. So you're going to pick one or multiple of these that you think is causing the water issue with this town. Okay. Then you're going to prepare, once the problem areas have been identified, draw several arrows showing how water flows through the contaminated area to the river. Okay, so someone in your group, whoever's in charge of Graph analysis will label and be like, look, see how this is where the area, this is how the water is moving in the map. Okay, and then this is really nice. It tells you exactly what needs to be in your paragraph. And then there's a rubric that I'm going to use to grade it based on this instructions. So paragraph 1 should include the principal responsible party. So who did it? Whose problem is it? What is your claim? So who did it? How do you know? It should also state how you are going to prove it through your data. So this is like introducing. I'm going to show you looking at the pH data, the groundwater data. We're going to look at the topographic map to show this. We're going to look at how the groundwater is flowing based on the topographic map. Okay? And then the next paragraph, there's 3 paragraphs. Paragraph 2 is you're going to look at the data in the table. So I would, if this was me, I would, once I have all of the information in my table, I would turn this in with my paper. So the easiest thing is you're going to take a picture of it and put it in your Google Doc or whatever you're using to write your report so that it's in the report, so that when someone's reading it, when I'm going to grade it, but if like the city was really reading this, it would be right there. They could go back and forth between the words and the figure. Okay. I think the thing that's going to make this the easiest is if you are really clear. You state everything. You tell them where to look. You explain anything you're thinking. So I'm looking at figure 1. Notice these sites are acidic. Notice these sites are basic. Notice the acidic site 18. It's next to the gas station. Notice, you need to lay out everything. Make it really obvious for them. If you think it's obvious and you don't think you should write it, I still think you should write it. And I think that'll make it easier to write, but also make it really clear that you have evidence of who has caused the problem. And I think that goes for any type of scientific writing. You have to lead the audience through all of your thoughts. They don't connect it themselves. You have to lead them, okay? Okay, let's see. So paragraph 2 is about the pH. So you're going to put the figure 1. You have this labeled. You walk them through the legend. You walk them through any arrows you added here. Show them where the acidic and basic parts are, and any conclusions that you're drawing from that. Paragraph 3 is the groundwater flow analysis. You also have that the color coded pH using the site map. So that's figure 2. What is it? Oh, 1 is, okay. So paragraph 2 is just the pH results. Paragraph 3 is the site map, explaining anything you found in the site map. Paragraph 4 is the topographic map, showing any arrows. You're showing like, oh look, it's a high pH and it's getting lower, but it looks like the pH is around here is being contaminated because of the topography, the slope. Okay. Walk them through any legends that you add. You could walk them through the, oh look, 95 is steep and there's really close lines together. That means there's a hill. Okay, these people don't know how to read this map, so you need to explain it. Okay, you are hired to explain this to them. In the final paragraph, bring everything back together. So say, remember, we talked about the pH data. Remember, there is a high pH next to this one. Remember, there is also high pHs next to, as it went downhill. Remember, downriver, there was a high pH. Tie that in. And then groundwater flow analysis. Remember that the pHs that were lower on the hill. Does that make sense? So you're walking through them. Remind them your evidence. Anything that you think supports your argument, and then conclude. So this is why it was the gravel pit, or whoever you decide. Restate your claim. In your report, you need to include your company's name, and then everyone who's in your group will turn in their own the same report. So if I'm working with someone, I'm gonna turn it in, but they also have to turn it in.
The same
Okay.
essay.
The same thing. Yes. Yeah. Requirement by River State. Yes. I know we can do groups and things on Canvas, but that's what they want you to do. Please save your file with first and last names of the writers. So, example, Sally Jones and Billy Bob. So, that's how you're going to save it. Okay, what else? Be sure to upload the paper to both students, 2 or 3, remember. Each student individually return in their own colored maps. Okay, so everyone has to do the map. That's why I gave everyone the map. So even if like you're in charge of doing some of the pH, everyone needs to fill in all of the pH and color code this. And you can be like, okay, yours was the best, we'll turn yours in the report. But everyone has to do this. Okay. Questions right now? Okay, let's go through the pre-lab. If you are working with someone who is not here, then you will want to maybe talk with them before you do the pre-lab. So, kind of think about, are you guys working in group or are you going to wait for I'll come back?
Is she gonna know how long 4 goes for? Do you know how long?
Sorry?
Do you know how long 4 goes for?
Till Sunday. So,
Okay.
our people should all be back on Monday. Yes.
She doesn't.
So think about people who are gone. Do you have maybe a group of 3 you can work in, or?
No, how was your day?
She was.
Okay. So the pre-lab is super fast. It's just like organizing your stuff. So if you want to hold off on doing the pre-lab, we'll just walk through it today. But it's just making sure that we all know who's in the right group. Does that make sense? So we have written it down. So yes, this would be okay to wait till Monday to do. It doesn't take that long. So what is the name of your company? Just have thought of that. And then who will be the lead on each of the following tasks? So who's gonna be the lead on the graph analysis? Who's gonna be the lead on the letter writer? Who's gonna be lead on the pH well table? So remember, everyone still has to analyze the graph, and everyone still has to turn in this well table, this table. Okay, but this is saying like who's gonna write this part in the paper. Okay, the letter writer doesn't write the whole paper. They're gonna write like the introduction and maybe the conclusion, and maybe make sure like it's formatted, looks good. Maybe they will do like the signature at the bottom or something. But the letter writer is like in charge of overall and like making sure everyone else does their part. But these other people, graph analysis, I think that they would write the paragraph on the graph analysis. And I think the pH well person would write the analysis on the pH well. Does that make sense? Okay. So make sure that you're kind of keeping duties equally. If you decide later that you need to switch responsibilities, that is okay. This is just helping us get an idea of what we need to be doing. Oh, also this will mark you wrong no matter what you put. I don't know, Weber State made it I don't know. So I will go back and give you points. Just make sure your names are in there. Question 3, if you have a 4th person, we are not doing 4th people. So put NA or don't put someone's name because we cannot work with 4 people. Weber State says we are working in groups of 2 or groups of 3. And they sent this before they decided that. So, question 4, how will the data gathering assignments be carried out? Who will be in charge of each water sample? So we have 27 water samples that we need to test. How are you going to divide that? And also if it doesn't exactly follow what you put in the box, that's okay. This is just like, we're planning for our lab. If it doesn't exactly follow this, I probably won't know, so that's okay. Describe your plan for color coding the map as outlined in step 1. The map in step 1. What are they talking about? Okay, I think they're talking about the pH measurements. Put these on a map with a colored pencil shading the areas of each pH. Create a key. So I think that's the site map. You're going to have your pHs, and then you're going to put this here. So it's asking you to think about, often we use red as acidic and blue as basic. Are you going to use that? And maybe like neutral is white. Often neutral is white. Maybe you're going to say, okay, I like green, and I want to include green. So you're going to, or like the pH paper says red, and then kind of green is basic. So you decide how you're going to label this. Okay, so what colors are you going to use? Or are you going to just shade it darker or lighter if it's more acidic or less acidic? So think about that. That's what it's asking. What's your plan? And then explain how the lines in a topographical map work. So we just talked about that. If they're closer together, that means it's steeper. If it's or a higher elevation, how do you know which direction is downhill? Well, the numbers on the side, if it's a lower number, then it is going downhill. So there's like a valley here. So it's high on this side and high on this side. So where the river is the lowest spot. Okay, questions. And that was the last question. Again, it will mark question 2 wrong. I just have to go back and give you points. And if you want to do this Monday, it doesn't take that long. And the lab also shouldn't take that long because we have 27 samples. We're just dipping pH paper in, checking the pH. That's it. So shouldn't be too bad. The biggest part of this lab is writing the report and analyzing the data. Okay. All right. Questions for me? Okay. So that's what we should expect on Monday. Any questions about Monday? So Monday?
Doing this on Monday?
We are doing this on Monday. Yep, in class. Yep.
We don't need like a report before, right? Or like before.
Oh, pre-lab. This is the pre-lab.
Well, no, sorry.
Procedure. Nope.
Okay.
Nope. Yep, we're going to take the tweezers, pick up a pH paper, dip the pH paper in. Make sure you don't contaminate the next sample. Pick another pH paper up, dip it in, write down the pH. So it'll be so fun. Okay, let's go to our notes for today. We're finishing up chapter 13. Is there anyone who doesn't have lab 13 notes? The note sheet. You don't, you got one? Okay. You grab one. Let me also really open Alex. Alex closed on me.
What? 87? What is this?
Okay. Anyone else see chapter 13? Okay, so we are going to talk about these things. So identifying cis and trans isomerism, drawing cis and trans isomers, predicting the reactants or products of alkene hydrogenation and hydration. So we're getting into real organic chemistry. All right, so we talked about last time we talked about isomers. We were talking about constitutional isomers, which is molecules that are only different by the way the atoms are connected. So they have the same chemical formula, they're just connected differently. Stereoisomers are isomers that only differ in the 3D arrangement of the atoms. So they're still connected the same way. The only thing is, if there's a double bond, one group is locked like if it's so this is the cis isomer, the groups are locked on the same side, that's cis. If they're locked on the opposite sides, that's a trans isomer. They're like across the double bond. Can you see that? These are constitutional isomers because there's a double bond at the first carbon, there's a double bond at the second carbon. So those are differently connected. Okay? This carbon has 2 hydrogens, this one has 3 hydrogens. They're both on the end, that's the difference. Okay? These ones are different only by, there's a double bond at the second carbon. The only difference is the 3D arrangement. So the methyl groups are across from each other. The cis isomers, they're on the same side. Okay? Remember, the double bond locks the bond. So those can't rotate. They can like wiggle, but they can't move. Unless you add enough energy to break the bond. And then they can move. Okay. Okay, we talked about that. So again, cis is on the same side, the biggest group's on the same side, trans is on opposite sides. Okay, so let's look at some examples of this. So this is oleic acid. So this molecule, it can rotate around all of these bonds, but this one is locked. So the biggest groups are locked on the same side of the molecule, that's a cis isomer. A trans isomer is where it's locked, they're locked on the opposite sides. Okay. Have you guys heard of trans fats? So the reason those are bad for us is because they're harder for our bodies to break down. They're more stable than cis fats. That's what it's talking about. It's talking about the double bond in those molecules. So if it's hard for our bodies to break down, versus easier, okay? And then saturated is, this one has no double bonds in the carbons, so that is saturated with hydrogens. That's a saturated fat. So that's what we're talking about when we're talking about that in a nutrition class. Okay, so we're going to skip our examples. We're going to go to reactions. We'll do the examples in Alex. Reactions of alkenes. So an addition reaction is just something is adding across the double bond. If you have a double bond, that makes the molecule more reactive, and then you can get it to react. So this is like what you would do in a year-long organic chemistry class. You predict products, you predict reactants. We do a little bit of naming, but this is mostly what organic chemistry is. You're trying to figure out, if I start with this, what can I end up with? Or I want to end up with this. What's some synthesis pathway to help me end up with this? And you follow all of these rules that people have found to do that. Okay, so an addition reaction is just where you have a double bond and some molecule, the bond here breaks and the bond here breaks, and then the X and Y add across the double bond. It's called adding across the double bond. So it has to go, these atoms in this molecule have to go on the carbons that were attached to the double bond. Okay. All right, so I don't want to see any groups somewhere else on the carbon chain. It has to be right where the double bond was. Okay. That's what makes it reactive, is the double bond. Okay, so these are some examples. We're going to look at hydrogenation and hydration, but these are some other ones. So if I'm doing hydrogenation, because I'm adding hydrogen across the double bond, we have to do this in the presence of a catalyst, and then the hydrogens just add to each side of the double bond, and now it's saturated. Okay. So basically, if you're looking at the skeletal structure, basically what's happening is the double bond is there, hydrogenation, the double bond is gone, because we don't draw hydrogens in a skeletal structure. Okay, the next one that they have up here is halogenation, which is you have like Cl2 or B2 or I2, and you're adding this halogen molecule across the double bond. So you have your double bond here, you start with the same starting material, you add this Cl2, and then you get Cl on each of the double bonds. Halogenation. This one is hydrohalogenation, because you get a hydrogen and a halogen across the double bond. And then the other one we're going to talk about is hydration, where you have water, and the water splits up and adds a hydrogen or hydroxide. So in one spot you get a hydrogen, other spot you get a hydroxide. This has to be in the presence of some kind of acid. That's the catalyst. It's an acid catalyzed reaction. Okay, so hydrogenation, we just talked about that. The hydrogen bond is going to break, the double bond is going to break, and then the hydrogen, each carbon gets one of those hydrogens. So we started with an alkene, and we end with an alkane. Okay. So some other things about this, I don't know if this is on your sheet. You have to have some kind of catalyst. You can pick your favorite hydrogenation catalyst. You can pick platinum, nickel, or palladium. That just makes the reaction go faster, and that's so you do need a catalyst. So one of the Alex topics is you have to say what else do you need? Oh, I need a catalyst. You have to pick one. Doesn't matter which one. If you want to saturate all the double bonds, for example, if you have 2 double bonds, you would need 2 hydrogen molecules. If you have 3 double bonds, you would need 3 hydrogen molecules. You need 1 hydrogen molecule for every double bond. Okay. All right, so if I'm looking at this one, how many hydrogen molecules would I need? So I have how many double bonds? So I just need 2 molecules of hydrogen.
Oh, that's
Because I would just add hydrogen across this one and this one. Okay. All right, the next thing is hydration, which is like hydrogenation, but you're adding a hydrogen on one side and a hydroxide OH on the other side. And this has to be in the presence of an acid catalyst. Let's see. Usually we write just H+, and that's what you'll see in Alex. Instead of H2SO4, they just put H+, an acid. Okay, so across this double bond, and again, the H and the OH have to be on where the double bond was. They can't just show up anywhere. They have to be on where the double bond was. Okay, so we also have to, if it's symmetrical like this one, that's easy. You just put H on one side, OH on the other side. If it's not symmetrical, then we have to follow this chemist's rule. It's called Markovnikov's rule, which is the OH adds to the more substituted carbon. So he discovered this. This is the pattern that it follows. If we have unequally substituted carbon, so this carbon has a hydrogen and a hydrogen, this carbon has a methyl group and a hydrogen, this is called the more substituted carbon. It has more carbons on the carbon. So the hydroxide, the OH is going to go on this carbon. The hydrogen is going to go on the less substituted carbon. That's the rule that we have to follow. Okay. Questions on that? So we have to watch for that when we're doing examples. Okay, let's go to Alex and we'll finish our topics. So let's see, we have to do this one. Drawing the cis or trans isomer of a small alkene. So draw the skeletal. So make sure you draw the correct structure. This one says skeletal. That means we're drawing the stick version. Make sure you draw the right one. The skeletal structure of trans 4,5-dimethyl-2-hexene. So I'm going to draw the parent structure first, hexene. 1, 2, 3, 4, 5, 6. Okay, this one's pointing up, this one's pointing down, so that's a good indication that there's 6 because it's even. If it's even, they point in opposite ways. If it's odd, they point the same way. Let's count 1, 2, 3, 4, 5, 6. I'm just double checking. The hexene is at the 2 carbons, so I'm going to put a double bond here. And then I have a 4,5 methyl. 1, 2, 3. There's one here, 4. And there's one here, 5. The other thing that I need to look at is it says it's a trans isomer. That means that if I draw a line through my double bond, one side is locked one direction and the other group is locked in the other direction. Can you see how this is the trans version? Okay, if I wanted this to be the cis version, I could pick up this one Now it's the cis version. Can you see how now these groups are on the same side of the double bond? This is back to they're on opposite sides. That's the trans version. Okay. All right, let's do some more. Draw the skeletal structure of trans 3-hexene. So hexene is 1, 2, 3, 4, 5, 6. Hexene 1, 2, 3. 1, 2, 3. Okay, so this is trans 3-hexene. That's all. Oh, so we'd have to decide if it's trans. So can you see if I draw a line through my double bond, one side is up and one side is down. So that's trans. Okay. If I wanted this to be cis, I don't, but if I wanted to, I could bring these on the same side. I could just pick them up and move them. Now they're on the same side. This would be the cis version of this molecule. This matters because even though they have all the same atoms and they're connected pretty similarly, they do have different physical properties and chemical properties. So like the trans fats, they're like almost the same as cis fats. They're just the trans version, the trans isomer, and that makes them unhealthy for us. So it does matter. Okay. How are we doing on this one? We haven't found a cis version. Let's find one. This one's also cis. Let's find one that's the cis version. Okay. Oh, my goodness. I think the trans ones are easier for me because you usually don't have to do anything. Okay. Cis 3-hexene. So 1, 2, 3, 4, 5, 6. 1, 2, 3. Oops. Oh, I'm trying to draw my double bond here at the 3 position. And then this is the trans version. So if I need the cis version, I'm just going to pick one side and drag it to the other side. I'm going to try to still make it follow my nice rules. That kind of looks funny. We'll see if Alex accepts that. But I can see my double bond. Both of these groups are on the same side. Okay. Let's see if there's another. Okay, I think we got those ones down. Okay, this one's cis 2-methyl-3-hexene. Oh. So I just draw the regular version, the zigzag. 1, 2, 3, 4, 5, 6. This one has a double bond in ene at 3 and a methyl at 2. Oops, I just want to draw this. And then this is the trans version because they're on the opposite sides of the double bond. So if I want it to be on the same side, I can just drag them. There we go. Okay, I think we got that. Let me know if you need help on practicing that one. Let's look at identifying cis-trans isomerism in a small condensed structure. Okay, so what this is asking you to do is to look at the molecule. And then for each molecule, could the molecule be a cis-trans isomer pair? So not are these pairs, could this have a twin isomer, okay? So what I look for is both sides have to have 2 different groups. So this one, because this carbon has 2 methyl groups, if I rotate that, it's still going to look the same. So let me try to draw this up here. I'll pull up my screen. Let me grab up the paper. So I'm looking at the top left one. I'm going to draw the skeletal structure. So I have something like this. Okay. So this cannot have a cis-trans isomer pair because for example, if I draw this, I can change this branch to be pointing down? Well, this is just a mirror image. So that's the same molecule. It's not an isomer if it's the same molecule. So because this has the same two groups on one side, that can't be a cis-trans isomer pair. So first one is no. Okay, let's go to the next one, the one to the right. And also I have OH, double bond. This side just has two H's, and this one has one H. So because this side has two H's, that can't be an isomer. It has to have two different groups on both sides, so that one can't have isomer pair. Okay, I'm going to do the bottom right. This one has two hydrogens on both sides, so that can't be a cis-trans isomer either. They're all hydrogens. We have to have two different groups on both sides. Oh, this one looks like this. We have a double bond with a methyl group, methyl group, methyl group. So also this one is very symmetrical. There's no way that we can rotate the methyl groups so that they're on opposite sides. So this question, none of them would be cis-trans isomer. They could not exist as a cis-trans isomer pair. Okay, let's look at another one. Let me try to write on a whiteboard. That might be easier to see. Okay, so again, we're looking for on the carbons connected to the double bond, there needs to be two different groups. So this one, the top left, we have carbon. Oh, and then we have CH3. Okay, I decided I don't want to write it like this. I'm going to go back to my skeletal structures. So I've got carbon. Oh, I'm going to do. Okay, let's draw the double bond. So you can see the double bond, and then off of the double bond we have. Too close. We have an OH, and then we have a methyl group. And then over here we have an OH and a methyl group. Okay, so this could exist as a cis-trans isomer if both sides have they have two different groups. If I flip which direction the OHs go, then this would be like the cis version and this would be the trans version. So this molecule could exist as a cis-trans isomer pair. Does that make sense? Okay, so basically look for, on each side, are there two different groups? Okay, let's look at the top right. Oh, this is the same molecule. So this is the same one. This is the isomer pair. We have two OHs and two methyl groups. On this carbon, we have OH and CH3. That's two different groups. And so each carbon connected to the double bond has two different groups. So this one is the isomer pair of this one. That doesn't have to be that way in this question. Okay, let's look at the bottom left. We have a double bond, and we have a chlorine group, and we have a chlorine group, and then we have a methyl group and a methyl group. So this would be an example that we could draw the chlorines pointing in opposite directions. We could switch which direction the methyl groups are going, and then this would be the cis-trans isomer pair. So this one could exist as a cis-trans isomer. This would be the trans, or this would be the cis version because they're on the same side. And then this would be the trans version. Okay, this cannot exist as a cis-trans isomer pair because this carbon has two identical groups. So if I draw this one out, we have our double bond, and then across the double bond we have, on the side we have OH, and on the side we have a methyl group. On this side we have a methyl group and a methyl group. That has two identical groups on this carbon. So if I'm like, oh, well, look, I could switch this. I could put this one pointing down. So that would be our attempt at getting that to be a different isomer. But if I just flip this back on top of it, like if I just rotate it, then it's the same molecule. This is the same molecule. Can you see that? That's the same molecule? You just rotate it, it's the same. Okay, so if it's the same, it's not an isomer. And the reason this one isn't is because there's two of the same group on the right carbon. You have to have two different groups on both of the carbons on the double bond. So that's what I check, is if I look and see, oh, different group, that could do it. This one, different group, that could be an isomer. This one has two of the same group, so that can't be. Okay, does that one make sense? You want to move to the next one? You want to do more of this one? More of this one, okay. Let me erase my board. Okay, so this first one on the left, top left, we've got our double bond. We have two methyl groups on this side. So because it has two methyl groups on this side, it can't be a cis-trans isomer. That has the same two groups. So this one, if I rotate chlorine and methyl group, I'll get something like this. And so then, can you see that's the same molecule? So that one, because it has two of the same group on one carbon, that can't be a cis-trans isomer. Okay, this one could be because we have two different groups on each of the carbons. So we've got our double bond. And this doesn't show me how it's drawn, but I can say like this is one version, and then this would be another version. So this would be the cis version, and this would be the trans version. So yes, this could exist as a cis-trans isomer pair. This one has two different groups on this side, but only one type of group on the left. So that's going to be like this one, but with OHs instead of methyls. So that one's not going to work. This all has methyls, so that one's not going to work. Does that make sense? So we're basically looking at the carbon. 1, 2 groups, 1, 2 groups, that one could work. This one has all the same group, that one can't work. So this one is yes, no. 2 methyl groups, no. This one could also work. Does that help?
Yeah.
Okay. 1, 2, 1, 2. 1 methyl, 2 methyl, same group. Then this one, so we could draw this one? Okay. So I've got, on the bottom left, I have a double bond. And then I have a methyl and a methyl. And a methyl. And if I rotate where the methyl and the hydrogen is, it's going to be like methyl, methyl, double bond, up.
Oh.
And it's like a mirror image. So if I just flip the molecule over, like on its back, then it would be the same molecule, not an isomer. All right. Okay. Are we okay with that one? Okay. All right. The next one. We did that one already. Do we have to name any? I thought we had to name one. Identifying. Maybe we don't have to name that. Okay. Identifying constitutional isomers, predicting the reactions or products. Okay. Predicting the reactants or products of an alkene hydrogenation. So this one has several different versions of this question, so just make sure that you have practiced all of them. It says, oh, I can't see what it says. I still can't see. One possibility for the mystery reactant. Oh, so we're supposed to come up with this reactant. So some kind of condensed structure, some molecule. We add one hydrogen and we get across a palladium catalyst, we get this molecule. So I usually just start by drawing this molecule and then putting in a double bond somewhere. Doesn't matter where the double bond goes. So let's see. This is just CH3. CH2, CH2, CH, methyl group pointing up, methyl group pointing over here. Oops, let's fix that. So I'm going to count 1, 2, 3, 4, up, down. Okay. So where do you want to put the double bond? Next to this one? Here?
Sure.
Here? Where were you talking? Maybe you could tell me what position. If we number it 1, 2, 3, 4, 5.
I thought it would look like the one in the instructional thing, but it doesn't. So
Oh.
I don't know where it goes.
Yeah, it doesn't matter.
Oh.
As long as you just put 1, you can put it anywhere.
Oh, okay.
So I'm gonna put it here because I just feel like that. If I put it here, then I have to go back and fix how many carbons or how many hydrogens. So I have to go down how many hydrogens. If I have a double bond, that decreases the number of hydrogens. So this is by 1. Oops, that's CH. So double check, make sure all of the carbons have the correct number of bonds. Remember, carbon has 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. Doesn't matter where the double bond is for hydrogenation. Okay, let's practice. There's a few different versions. This one says, for the following organic reaction, identify the mystery reactant, which is R. Its stoichiometric coefficient, that's how many you need of that, the ratio, and any other substance that must be present. Okay, so if we look at this molecule, how many double bonds? So how many hydrogens do I need? Yep, so N is 2. So that's all I have to do. 1, 2, that number is 2. Easy. Just remember how to do it. Chemical formula of R. This is hydrogenation. You can tell that because the double bonds are disappearing. So this must be H2. And does there need to be an X and then something else here? Yes. In hydrogenation, yes, we always have to have a catalyst. And you can pick nickel, palladium, or platinum. I'm gonna pick platinum. Nope. You get to pick your favorite hydrogenation catalyst. Okay. This one, predict the product of this organic reaction. Oh, okay, so what happens if we add 2 hydrogens across this molecule? The double bonds are gonna go away, and we're gonna have more hydrogens. So everywhere there's a double bond, each carbon connected to a double bond is going to increase in hydrogen. Only the ones connected to the double bond. So the other way to think about this is this would be saturated. Every carbon would be full of either hydrogen or it's already there carbon bonds. Single bonds only. Okay, so I'm just going to start over here. This we would change to a methyl group because we're adding the hydrogen here. Then we're adding another hydrogen here, so this is CH2. We're not adding hydrogen here because this didn't have a double bond. This one is not getting anything. Oh, see, it's connected to a double bond, so it's going to go up by hydrogen 1. This one didn't have a double bond, so this carbon is just staying the same. And then, let's see, where are we? This one, or are we? Yeah, we're here. This one's going to get an extra hydrogen, and this one's going to be regular. Let's see, let's go back here. This one needs just CH, right? CH. Thank you. CH. Is this one just CH also? This one just CH. Yeah, because it just goes up by 1. I was trying to make it go up by 2. Okay, so let's double check. This carbon has 3 bonds and a hydrogen, 3 bonds and a hydrogen. 2 bonds and 2 hydrogens, 1 bond, 3 hydrogens, 1 bond, 3 hydrogens, 1 bond, 3 hydrogens, 1 bond, 3 hydrogens, 1, 2, 3, 4, 5. I'm making sure that I have the same number of carbons in my chain. 1, 2, 3, 4, 5. Should be good. Okay. So just make sure those condensed structures get people. Make sure you check. Make sure they have, each carbon has 4 bonds. Let's see. Okay, this is another one where we're predicting the reactant. It doesn't matter where the double bond goes. It can go anywhere. I'm gonna put it over here. Put it in the middle, doesn't matter. Okay. All right, you think you can do that? Okay. The last one is the hydrogenation, predicting the reactants or products of hydrogenation. This is this is our last topic that we have to learn this year. That's kind of exciting. This one, remember the double bond makes it react. So when we're adding water across this double bond, one side gets OH, one side gets H. And it has to be on these carbons. It can't show up over here. It has to be just on the double bond. Okay, that's one of the things that people do on the test is they just put the hydrogen and the hydroxide somewhere. And it's like, no, it has to go on the double bond. That's what's making it react. Okay, so this one's very tedious. Let's go ahead and draw it out. So we've got CH3, CH2. This one has the double bond. What we have to decide is so we know hydrogen is going to add on one side and the hydroxide is going to add on the other. According to Markovnikov's rule, the OH goes to the more substituted carbon on the double bond. So is that going to be the top carbon or the one in the chain? That one's going to be less substituted. This one, can you see how this one has a carbon and a carbon? And this one just has 2 hydrogens. This one's more substituted. So we'll put our carbon here. And the OH is going to come off of this carbon. And then we still have this double bond up here. Or no, we don't have the double bond. We have this carbon that was at a double bond. That's going to get the hydrogen. So can you see how instead of 2 hydrogens, I put another hydrogen there because that's the H from the water. And that's the OH from the water. Okay. And then we're just going to draw the rest of the structure as normal. I'm going to be really careful so that I get this right and I don't get it wrong because I drew something else wrong. Oh. Okay, questions on that? I guess we better check, make sure. Okay, more practice. Give one possibility for the mystery reactant. Okay, so we have to draw this molecule, but we have to draw it with a double bond somewhere. The way the OH is attached, it does not matter where you put the double bond here. So I could put it in the middle, or I could put it at the end. Doesn't matter. Which one should we try? The end, okay. So I'm gonna put my CH2, I'm gonna put my double bond here. Oops, let's see. Just, yeah, CH. CH2, CH3. Okay, I'm gonna check. This carbon has 1 bond and 3 hydrogens. This carbon has 2 hydrogens and 2 bonds. This carbon has 3 bonds and 1 hydrogen. This carbon has 2 hydrogens and 2 bonds. So it is good to go. I'm gonna just check. Okay. Predict the major product of this organic reaction. So if it has water, again, this is going to be, so this is a kind of tricky topic on the test. I think this also might show up on the final. the OH and the H have to go on the double bond. And then the OH has to go on the more substituted carbon. So for this one, the OH is going to go on this carbon on the double bond because it's more substituted. And the H is going to go over here. And the double bond like disappears. Okay, so I'm going to draw kind of what they show. And then instead of a double bond, I'm going to have OH and H. But I'm not going to draw the H because it's a skeletal structure. Okay. I was going to tell you, you have to recognize that water with a double bond means that you're going to get OH. Okay. You have to know that if I have a double bond and the double bond goes away, that means that you are adding hydrogen. That's a hydrogenation. So you have to distinguish between these two. Okay, let's do one more of these. Okay, this one doesn't matter. We're drawing the reactant. So this one's going to be propene. No matter how I draw that, the OH will add here. Okay, let's do another one. That one was easy. Predict the major product. Okay, so I'm adding water. Okay, so I have to know that it's going to have one OH on one side and an H on the other side of the double bond. So we're going to draw CH3. I'm going to put this one is symmetrical, so it doesn't matter. I'm going to put the H on this one, CH2. I'm going to keep the CH here, then I'm going to put the OH here. So the OH is adding, I'm saying it's going to add to this carbon. It's symmetrical, so it doesn't really matter. And then CH3. Then double check. Make sure all of your carbons have 4 bonds. Make sure the OH added to the more substituted carbon, but it doesn't matter here because it's symmetrical. Okay. All right, that is all of our topics for the whole year. So make sure, so now you could really get to 100% pie progress because we're done with our topics. So you should work on that. The more topics that you have open for the final, the easier it is going to be to review for the final. Okay, so do your best. Work on that. If you have questions, if you get stuck, I can help you through those topics that you're getting stuck on, okay, so that they're open. Also, remember your signature assignment is due on Tuesday, so make sure you get that done.